So imagine we have something like this in 3 dimensions. We can address this question in the higher dimensions, but again, they will be the same. This problem will be relying a lot on our previous discussion on the distance from a point to a plane, and that's why they will have the same double approach. Yeah, two approaches. One of them which works in 3 dimensions, and the other one which works everywhere. Here's my 2 lines. So each of them can be. We can assume that each of them. So one of them I'll call little L1, and assume my line is given by the vector equation like this, and the second one is L2, given by the vector equation like this. So my question is if I want to find the distance between these 2 lines, again, I can follow the same argument I did just now, 30 minutes ago. Remember, if I want to find the distance between these 2 lines, again I can raise the question of minimization. What should I minimize this time? Well, this time I have to minimize this function. Well, this time I use the not xy but lambda and mu for the arguments. And just the reason for that is because lambda here is a parameter, and I replaced this parameter with another Greek letter, with letter mu. This time I have to minimize something like this. If I minimize something like this, that will be the distance between my lines. If I picture this on my graph, here it is. So I take all different points on my 2 lines, connect them, and I try to measure the distances, and I try to minimize these distances. Again, from the analytical point of view, you're looking at the function of 2 variables, which, if you expand everything, will be probably, again, circular paraboloid. So it will be square function of 2 variables. Minimization of such a function, it's a difficult task in general. However, right now I don't even need to expand this, because now I can rely on what we did with you on the previous slide. Yes. Say again. I mean, the question is why the mu here rather than lambda, or the other way around. So you want me to put here mu? That will do as well. I don't know, when I was first typing this, normally we just, when you type an equation of a line, you just put any parameter which comes first to your head, right? T, lambda, s. So lambda came to my head first, I typed in lambda. That's the reason lambda is in there. But then when you do something like this, you no longer can use the same name for the parameter in here and in here. So I have to distinguish them for the obvious reasons, right? Because otherwise these parameters will be connected together. You no longer will have all possible distances. So if you want to see mu here, no problem. But it's a symbolic change. It's nothing. You can use lambda, mu, ts, whatever. Thanks for the question anyway. So when you address the question like this, finding the distance between the line and the plane, little trick, and I'll show this trick in a second, will actually reduce the question totally towards the distance between the point and the line. Do you know the trick? There's a little beautiful trick which converts the problem of distances between the lines to the problem distance between the point and the plane. Here it is. What I will do is this. I'll take this line and I'll drop it down here, like this. And then rather than finding the distance between my lines, I'll find the distance between any point on this line to the plane running through my 2 new lines. I mean, one old and one new line. From the geometrical point of view, that's identical question, isn't it? And we know how to solve the previous one. Are you with me? By dropping this line down here, you no longer need to consider the distances between the lines, but instead we will find the distance between the point here to a plane around my 2 lines. And we know, in principle, we know how to do that. For that, we have 2 methods, 3-dimensional method and high-dimensional method. So, do I have a picture? I think I have a picture for that. So, the solution to the question how to find the distances between the lines will be based on this. I'll drop the line down here, choose a point on my line, and I find the distance from the point to my new plane. So the alternative solution to this, and that's a pure algebraic solution, it will go like this. Distance, which we know it's the length of the vector, is my u vector, and the s is a plane like this. And the u vector can be taken as a difference of a1 and a2. Here it is. So the alternative solution basically will be just following these two lines. I don't know that. It's a illusion from the picture, actually. It's not necessarily will be on that line, no. It's just because, I'm sorry, it's just because the picture here is a perpendicular. At this point, the base of this perpendicular, it may end up anywhere. It may end up here, it may end up here. So don't be just confused by the fact that it ended up here, just because when I was making this picture, of course, it was easier for me to make the orthogonal picture, using the orthogonal parallelepiped for that. But in principle, this line can end anywhere, and not necessarily on this dashed line. So just don't rely on this information which seems obvious to you from this picture. No, it's not going to end up like this. Any more questions? It may end up anywhere, but it's irrelevant actually. I mean, who cares where it will end up? In fact, your job is to find the distance, and that's how you can do it. Yeah, and here's the version of the solution in the three-dimensional version of this solution. That's the one which probably you will be using most often. In 3 dimensions, you can drop the perpendicular not here. You can first find the vector perpendicular to your to your B1 and B2 this time. These are the directional vectors of my lines. If you find such a vector, H, if you find such a vector, then the distance alternatively can be computed like this. It will be projection of the difference between the position vector here and the position vector here, and this time you will project onto joint perpendicular vector. These sort of questions, they are in plenty in tutorial book.